soft, deep atmospheric rumble, cinematic orbital view of Earth from space. Narrator calm cinematic tone. Something strange is happening high above Earth. Not in the oceans, not on the surface, but in the atmosphere itself. Scientists are now observing unusual shifts spreading through the layers that protect all life on this planet, from the jet stream to the ionosphere, all the way to the edge of space. The atmosphere is expanding, circulation patterns are changing, and energy from the sun is interacting with Earth in ways we are only beginning to understand. What you're about to see isn't science fiction. It's real atmospheric physics unfolding right now. Slow orbital descent through glowing atmosphere. Before we begin, make sure to like the video, subscribe to the channel, and turn on notifications, because this is one story that is far from over. Let's go higher than weather and explore the invisible system surrounding our world. The outermost region of Earth's atmosphere extends into a vast diffuse zone known as the exosphere, where the boundary between air and space becomes increasingly indistinct. In this region, gas particles are so widely separated that collisions between them occur only rarely, and each particle moves along long curved paths influenced primarily by Earth's gravity and incoming solar energy. The exosphere begins above the exobase, a notional level, where the atmosphere becomes thin enough that particles can travel significant distances without interacting with one another. Above this level, motion is dominated by ballistic trajectories, meaning particles follow paths similar to thrown objects arcing through space under gravity before occasionally encountering another atom or escaping entirely. Hydrogen and helium are the most common constituents in this region, not because they are abundant at lower levels, but because their light mass allows them to rise and persist at extreme altitudes. Heavier gases are less common here, as they tend to remain closer to the denser layers below. Over long timescales, some of these light atoms gain enough energy from solar radiation and particle interactions to exceed Earth's escape velocity, slowly drifting away into interplanetary space. This gradual loss process is extremely slow on human timescales, but significant over geological periods, contributing to the long-term evolution of atmospheric composition. The exosphere is also a region of constant interaction with the solar environment. Streams of charged particles emitted by the sun, known as the solar wind, pass through this outer layer and occasionally interact with neutral atoms. When such interactions occur, electrons can be exchanged, altering the charge state of particles and subtly influencing their trajectories. These processes are not dense or violent in the conventional sense, but they are persistent, shaping the outer boundary of Earth's atmospheric envelope through continuous low-intensity exchange of energy and matter. Radiation from the sun plays a central role in defining the physical state of this region. Ultraviolet and extreme ultraviolet light carry enough energy to heat and energize the sparse particles present, increasing their velocities and affecting their likelihood of escape. Because collisions are rare, this energy is not quickly redistributed as it is in lower atmospheric layers. Instead, individual atoms absorb energy directly, becoming temporarily more energetic, before either stabilizing or leaving Earth's gravitational influence entirely. Within this thin environment, the concept of temperature becomes less intuitive. In denser layers of the atmosphere, temperature reflects the average kinetic energy of many interacting particles. In the exosphere, however, the scarcity of collisions means that temperature varies depending on measurement method and particle behavior. A single energetic atom does not necessarily represent the state of its surroundings, as there is little collective behavior to define a uniform thermal condition. Despite this, scientists still describe temperature in terms of particle energy distributions to maintain consistency with lower atmospheric models. The exosphere also forms the outer part of what is sometimes referred to as the geocorona, a faint extension of hydrogen atoms surrounding Earth. This structure is extremely diffuse and invisible to the naked eye under normal conditions, yet it can be detected through specialized observations of ultraviolet light scattered by hydrogen atoms. The geocorona extends far beyond the denser atmospheric layers, gradually blending into the interplanetary medium, where solar particles dominate the environment entirely. Earth's gravity continues to exert influence throughout this region, though its effects are weakened by distance and the high kinetic energy of particles. Some atoms follow closed or semi-closed orbits around the planet, while others follow open trajectories that lead them away permanently. This balance between retention and escape defines the structure of the exosphere and ensures that it remains a dynamic boundary rather than a fixed shell. The interaction between neutral atoms and charged solar particles creates subtle variations in density and motion within the exosphere. Charge exchange processes can occur when a fast-moving ion from the solar wind captures an electron from a neutral atom, transforming both participants and altering their paths. These interactions contribute to the gradual reshaping of particle distributions without producing large-scale turbulence or visible structure. Over time, the exosphere acts as a slow interface between Earth and space, regulating the exchange of matter at the most distant edge of the atmosphere. It is neither fully atmospheric nor fully interplanetary, but instead exists as a transitional domain where physical processes shift from collision-dominated behavior to collisionless motion. This makes it a key region for understanding how planetary atmospheres interact with the space environment. Despite its extreme thinness, the exosphere plays a role in satellite dynamics, as artificial objects passing through this region encounter minimal but non-zero resistance. Even faint traces of atmospheric drag can accumulate over time, gradually altering orbital paths. This effect is subtle yet important for long-duration missions as it influences orbital decay and the long-term stability of near-Earth space. The outer boundary of the exosphere does not have a sharp edge. Instead, it gradually fades into space as particle density decreases and the influence of Earth's atmosphere diminishes. This gradual transition reflects the continuous nature of atmospheric structure, where each layer blends into the next without abrupt separation. At the highest reaches, Earth's influence persists only through gravity and rare particle interactions, marking the final stage of atmospheric presence before the dominance of interplanetary space becomes complete. The behavior of this outer layer also changes gradually with solar activity, as increases in ultraviolet radiation raise particle energies and enhance the probability that the lightest atoms reach escape velocity. During quieter solar conditions, atmospheric loss slows, maintaining a more stable balance between retention and escape. Near this boundary, Earth's magnetic influence indirectly shapes the motion of charged particles, arriving from space even though the exosphere itself remains largely neutral. Interactions between solar wind ions and neutral atoms can alter particle trajectories through charge exchange, creating subtle shifts in local particle distributions without forming dense structures. A key mechanism of atmospheric loss in this region is thermal escape, where individual atoms gain sufficient kinetic energy to overcome Earth's gravitational pull. This process, most effective for hydrogen, gradually influences long-term atmospheric composition. Observations from satellites and remote sensing instruments detect faint ultraviolet scattering from hydrogen atoms, allowing scientists to map density variations and track how this outer layer changes over time. Above the mesosphere and below the highest reaches of near-Earth space, the thermosphere forms a region where atmospheric behavior shifts sharply under the influence of intense solar radiation. In this layer, the density of air remains extremely low compared to lower altitudes, yet it is significantly higher than the exosphere, allowing more frequent interactions between particles. Energy from the sun, especially in the form of extreme ultraviolet and X-ray radiation, is absorbed directly by the sparse gases present, leading to a strong increase in particle energy with altitude rather than the decrease seen in lower atmospheric layers. The absorption of high-energy solar radiation causes atoms and molecules in this region to undergo ionization, a process in which electrons are stripped away from neutral particles. This creates a mixture of charged and neutral particles known as a plasma, though in this context it remains weakly ionized compared to laboratory or astrophysical plasmas. Oxygen is one of the most significant contributors in this region, as atomic oxygen becomes abundant at these heights due to the dissociation of molecular oxygen by solar radiation. Nitrogen also participates in these processes, though it is generally more stable and requires higher energy input for ionization. As particles absorb energy, the concept of temperature in the thermosphere becomes distinct from that in denser atmospheric layers. Temperature here reflects the kinetic energy of individual particles rather than the heat felt by an object, because collisions are still relatively infrequent. A thermometer placed in this region would not register a meaningful temperature in the traditional sense, since there are too few interactions to establish equilibrium. However, particle velocities can become extremely high, corresponding to temperatures that can reach thousands of degrees Celsius when measured statistically. Despite these high kinetic energies, the thermosphere would not feel hot in the conventional sense, because the low density of particles means that there is very little transfer of energy to surfaces. A human body or spacecraft passing through this region would just not experience heat in the same way as within denser air, since there are too few collisions to transfer significant thermal energy. Instead, the environment is defined by radiation and charged particle dynamics, rather than direct conductive or convective heat transfer. The ionization process in this layer plays a central role in shaping large-scale electrical properties of Earth's upper atmosphere. When solar radiation strips electrons from atoms, it creates regions of positive ions and free electrons that respond to electromagnetic forces. These charged particles are influenced by Earth's magnetic field, which organizes their motion into curved trajectories along magnetic field lines. This interaction between charged particles and magnetic structure is fundamental to many of the visible and measurable phenomena associated with this atmospheric region. One of the most prominent manifestations of these processes is the formation of auroras. These luminous displays occur when energetic particles originating from the Sun are guided by Earth's magnetic field toward polar regions, where they collide with oxygen and nitrogen atoms in the upper atmosphere. The collisions excite these atoms, causing them to release energy in the form of light as they return to lower energy states. Oxygen emissions often produce green and red light depending on altitude and energy conditions, while nitrogen contributes blue and purple tones. These emissions are not continuous but vary with the intensity of incoming solar activity and the configuration of the magnetic field. Auroral processes occur primarily near polar regions because Earth's magnetic field lines converge there, allowing charged particles to enter the atmosphere more easily. In equatorial regions, these particles are more likely to be deflected, limiting direct interaction with atmospheric gases. The structure of the magnetic field therefore determines the spatial distribution of energy deposition in the thermosphere, concentrating dynamic activity in specific zones while leaving others relatively undisturbed. The thermosphere also responds dynamically to changes in solar activity over time. Periods of increased solar output, such as solar maximum phases within the solar cycle, lead to stronger radiation input and higher rates of ionization. During these times, the density and extent of the thermosphere can expand outward, increasing atmospheric drag on objects in low Earth orbit. Conversely, during quieter solar periods, reduced energy input allows partial contraction of this layer, altering the conditions experienced by satellites and other artificial structures. Within this region, the balance between ionization and recombination continuously evolves. Ionization adds free electrons and ions to the environment, while recombination allows these charged particles to rejoin and form neutral atoms again. This ongoing cycle maintains a dynamic equilibrium that depends heavily on solar radiation intensity and local particle density. The rates of these processes vary with altitude, time of day, and geographic location, creating a highly variable environment even at similar heights. The thermosphere also exhibits strong diurnal variation, meaning its properties change between day and night. On the sunlit side of Earth, ionization rates increase due to direct exposure to solar radiation, leading to higher electron densities and more active plasma behavior. On the night side, reduced solar input allows recombination to dominate, decreasing ionization levels and altering the electrical conductivity of the region. These differences contribute to complex global circulation patterns in the upper atmosphere. Energy input from the sun does not distribute evenly across this layer. Instead, it is modulated by both atmospheric composition and magnetic field geometry. Regions with stronger magnetic coupling experience more intense particle interactions, while others remain relatively quiet. This uneven distribution of energy contributes to the formation of structures that vary in both time and space, reflecting the dynamic coupling between solar activity and Earth's atmospheric system. Although the thermosphere is extremely thin compared to lower atmospheric layers, it plays an important role in mediating the interaction between Earth and space. It acts as a region where incoming solar energy is absorbed and transformed into electrical and kinetic processes rather than directly reaching lower altitudes. This energy transformation helps regulate how solar radiation influences the overall atmospheric system. At the upper boundary of this region, particles gradually transition toward more collisionless behavior, as density decreases, further blending into the conditions of the overlying exosphere. At the lower boundary, increasing density leads to more frequent collisions, marking a gradual transition into the mesosphere. These boundaries are not sharply defined, but instead represent zones of gradual change in physical behavior, where the dominant processes shift from radiation-driven ionization to collision-driven thermal exchange. The thermosphere remains a region of continuous variability shaped by the interplay of solar energy, magnetic structure, and atmospheric composition. Its behavior reflects both external forcing from space and internal responses within Earth's atmospheric system, maintaining a dynamic balance that evolves over multiple timescales, from daily cycles to long-term solar variations. The ionosphere forms a distinct electrically active region, embedded within the upper atmosphere, overlapping portions of the thermosphere and extending downward into higher layers of the mesosphere. It is defined not by a single altitude range, but by the presence of a significant population of ionized particles created when solar radiation removes electrons from neutral atoms and molecules. This process produces a medium that conducts electricity weakly, but consistently, allowing electromagnetic forces to shape the motion of charged particles across broad spatial scales. In this region, solar ultraviolet radiation and X-ray energy provide the primary source of ionization. When high-energy photons strike oxygen and nitrogen, they transfer enough energy to detach electrons, creating positively charged ions and free electrons. These particles coexist in a delicate balance, constantly forming and recombining depending on local energy conditions. The result is a plasma-like environment, though far less dense and more variable than laboratory plasmas or those found in stars. The ionosphere is structured into broad layers that reflect differences in ionization, efficiency, and atmospheric composition with altitude. At lower heights within this region, ionization is weaker due to greater atmospheric density that increases recombination rates. At higher altitudes, ionization becomes more sustained because particles are more widely spaced, allowing charged states to persist longer before neutralization occurs. These gradients produce a layered electrical structure that varies in strength and density throughout the day and night. Electrons in the ionosphere play a central role in shaping its physical behavior. Because electrons are much lighter than ions, they respond rapidly to electromagnetic fields, moving quickly along magnetic field lines and contributing to the region's electrical conductivity. This mobility allows the ionosphere to support large-scale current systems that connect different regions of the atmosphere and even couple to processes occurring in near-Earth space. Ions being more massive respond more slowly and provide the bulk of the charged mass within the system. Earth's magnetic field strongly influences particle motion in this region. Charged particles tend to spiral along magnetic field lines, creating guided pathways that direct energy and momentum through the upper atmosphere. This alignment produces anisotropic behavior, meaning properties vary depending on direction relative to the magnetic field. As a result, the ionosphere is not uniform but structured by the geometry of Earth's magnetism, which shapes how energy flows across different latitudes. One of the most important effects of the ionosphere is its interaction with radio wave propagation. Radio signals transmitted from Earth can reflect or refract within this charged layer, allowing long-distance communication by bouncing signals over the horizon. The efficiency of this reflection depends on electron density, which varies with solar activity time of day and atmospheric conditions. During periods of strong solar radiation, higher electron densities can enhance or disrupt signal paths, altering communication reliability across large distances. The ionosphere also exhibits significant temporal variability. During daylight hours, solar radiation increases ionization rates, leading to higher electron concentrations and stronger electrical conductivity. At night, in the absence of direct solar input, recombination reduces electron density, weakening the ionized structure. This daily cycle creates predictable fluctuations that influence both natural atmospheric processes and human technological systems that depend on ionospheric stability. In addition to daily variation, the ionosphere responds to longer-term solar activity cycles. Periods of increased solar output enhance ionization levels, expanding the region and increasing its electrical complexity. Conversely, reduced solar activity leads to contraction and lower electron densities. These variations are not uniform across the globe, as differences in magnetic field strength and atmospheric composition produce regional asymmetries in ionospheric behavior. The ionosphere is also closely linked to energetic events originating from the Sun. When bursts of solar particles such as those associated with solar flares or coronal mass ejections reach Earth, they can dramatically increase ionization rates and disturb the existing balance of charged particles. These disturbances propagate through the ionosphere as waves and irregular structures, temporarily altering its electrical properties and affecting the transmission of electromagnetic signals. Within this region, recombination processes continuously work to restore neutrality. Free electrons eventually recombine with positive ions, forming neutral atoms or molecules again. This balance between ionization and recombination maintains the dynamic equilibrium of the ionosphere. The rates of these processes depend strongly on altitude composition and energy input, leading to complex spatial and temporal patterns of variation. The ionosphere also interacts with neutral atmospheric layers below it. Energy transfer occurs through collisions between charged and neutral particles, allowing momentum and heat to be exchanged across regions that are otherwise governed by different physical principles. This coupling means that changes in the ionosphere can influence lower atmospheric dynamics and vice versa through indirect but persistent interactions. Electric currents flowing through the ionosphere are part of larger global circuits that connect different regions of Earth's atmosphere. These currents are driven by the movement of charged particles under the influence of both solar radiation and magnetic forces. As these currents flow, they generate secondary magnetic fields that can be detected on the ground, revealing the presence and structure of ionospheric activity, even without direct atmospheric measurement. The ionosphere does not have a fixed boundary. Instead, it merges gradually with the thermosphere above and the mesosphere below, with ionization levels decreasing progressively rather than ending abruptly. This gradual transition reflects the continuous nature of atmospheric structure, where physical properties shift smoothly rather than discontinuously. Despite its tenuous density, the ionosphere plays a crucial role in linking Earth's surface environment with near-Earth space. It acts as a mediator of energy transfer, electromagnetic propagation, and particle dynamics, forming an electrically responsive shell that is constantly shaped by solar influence. Its behavior reflects both local atmospheric conditions and distant solar activity, making it a dynamic interface between Earth and space. Below the ionosphere and within the upper reaches of the thermosphere, the atmosphere enters a transition zone where neutral particles begin to outnumber ionized ones, yet still remain influenced by residual solar energy. This region is not defined by sharp physical boundaries, but by gradual changes in particle density, collision frequency, and energy exchange. It marks a shift from plasma-dominated behavior toward increasingly neutral gas dynamics, where collisions become more frequent and begin to regulate motion more strongly than electromagnetic forces. In this layer, atomic oxygen remains a dominant species formed through the dissociation of molecular oxygen at higher altitudes. Nitrogen is also present primarily in molecular form and becomes increasingly stable as altitude decreases. The balance between these gases reflects the gradual return to a collision-dominated environment where chemical reactions depend more on thermal motion than on radiation-driven ionization. As altitude decreases within this transition region, the frequency of particle collisions increases steadily. Each collision allows energy to be exchanged between particles, leading to a more uniform distribution of kinetic energy. This process gradually restores the conditions necessary for classical thermodynamic behavior, where temperature becomes a meaningful measure of average particle motion. Unlike higher regions where energy is stored in individual particles here, it becomes shared across many interactions. Solar radiation still penetrates this region, but its effects are reduced compared to higher altitudes. Extreme ultraviolet radiation is largely absorbed above, leaving weaker, ultraviolet and scattered energy to influence chemical processes. This diminished radiation input allows recombination to become more effective, gradually reducing the number of free electrons and ions. As a result, electrical conductivity decreases and neutral gas behavior becomes more dominant. The motion of particles in this region is influenced by both residual electromagnetic forces and increasing atmospheric density. Charged particles that descend from higher layers encounter more frequent collisions, which slow their motion and encourage recombination with electrons. This process transforms ionized particles back into neutral atoms or molecules, contributing to the gradual fading of plasma characteristics with decreasing altitude. Thermal structure in this region becomes more stable compared to higher layers, though it still reflects solar-driven variability. Daytime heating from above can slightly increase local temperatures, while nighttime cooling allows energy to radiate away more efficiently. These variations are less extreme than in the ionosphere but remain important for maintaining vertical energy balance within the atmosphere. Chemical reactions in this layer occur primarily through neutral-neutral interactions, where atoms and molecules collide and exchange energy without requiring ionization. These reactions are slower than ion-driven processes, but become increasingly important as ionization levels decrease. Oxygen atoms can recombine to form molecular oxygen, and nitrogen molecules remain largely stable, contributing to the chemical consistency of the region. This transitional environment also plays a role in vertical energy transport. Energy from higher layers is gradually transferred downward through collisions, while energy from lower layers can move upward through turbulent mixing. These opposing flows create a complex balance that influences temperature gradients and atmospheric stability across multiple altitudes. Although electromagnetic influences weaken in this region, they do not disappear entirely. Weak electric fields can still exist due to residual ionization and the movement of charged particles. However, these fields are less structured and more diffuse than those in the ionosphere, reflecting the gradual loss of large-scale electrical organization. The density gradient in this layer is smooth but continuous. As altitude decreases, the number of particles per unit volume increases exponentially, leading to more frequent interactions and stronger coupling between gas components. This increasing density is a key factor in the transition from collisionless or weakly collisional regimes above to fully collisional behavior below. Momentum transfer becomes increasingly efficient in this region. Each particle collision redistributes energy and motion, allowing large-scale atmospheric flows to develop more coherent structures. This process contributes to the formation of broader circulation patterns that extend downward into the mesosphere, linking upper atmospheric dynamics with lower layers. The transition zone also acts as a buffer between highly variable solar-driven processes above and more stable atmospheric conditions below. Energy fluctuations from solar activity are gradually damped through collisions, reducing their intensity before they reach denser atmospheric regions. This buffering effect helps stabilize the overall atmospheric system. Gravitational influence remains constant throughout this region, but its effects become more evident as particle motion slows due to increased collisions. Heavier particles tend to settle more effectively, while lighter particles can still reach higher altitudes through thermal motion. This separation contributes to subtle compositional gradients that vary with height. The boundary between this region and the mesosphere below is not distinct but defined by a gradual increase in atmospheric density and a corresponding decrease in ionization. As the atmosphere continues downward, radiative effects weaken further, and thermal processes become fully dominant in shaping atmospheric behavior. The mesosphere occupies a middle region of the atmosphere where temperature decreases with altitude, reaching some of the coldest values in the entire atmospheric system. This cooling trend results from decreasing absorption of solar radiation and increasing efficiency of infrared radiation loss to space. In this layer, energy balance is shaped primarily by radiative cooling, rather than direct solar heating, creating a thermally distinct environment compared to the layers above and below. Atmospheric density in the mesosphere is significantly higher than in the thermosphere and ionosphere, yet still far lower than near the surface. This intermediate density allows collisions between gas molecules to occur frequently enough to maintain thermodynamic equilibrium, while still being sparse enough that radiative processes remain important. The combination of these factors produces a region where both molecular motion and radiation contribute to temperature structure. Molecular nitrogen and oxygen dominate the composition of this region. Oxygen remains largely in molecular form as the energy required to dissociate it into atomic oxygen is less available here than at higher altitudes. Nitrogen molecules are highly stable and persist throughout the mesosphere, providing a consistent background for atmospheric interactions. Trace gases, including water vapor and ozone remnants, also influence local chemical processes, although in much smaller quantities. As altitude increases within the mesosphere, temperature continues to fall until it reaches a minimum near the upper boundary. This cold region, known as the mesopause, represents the lowest temperatures found in Earth's atmosphere. The cooling occurs because molecules in this region lose energy through infrared radiation faster than they gain it from incoming solar energy or from lower atmospheric layers. Despite the general cooling trend, the mesosphere is not thermally uniform. Local variations in temperature occur due to atmospheric waves, including gravity waves, that propagate upward from lower layers. These waves carry energy and momentum, causing periodic heating and cooling as they move through regions of differing density. When these waves break, they deposit energy and contribute to localized turbulence. Meteoric material entering Earth's atmosphere also interacts strongly with the mesosphere. Small meteoroids, often no larger than grains of sand, encounter increasing atmospheric resistance as they descend into this region. Frictional heating caused by collisions with atmospheric particles leads to rapid vaporization, producing visible streaks of light known as meteors. This process injects metallic atoms such as iron and magnesium into the mesosphere, altering its chemical composition on a continuous basis. The presence of meteoric debris contributes to the formation of thin layers of ionized and metallic particles, even though overall ionization levels remain low compared to higher regions. These layers can persist temporarily, influenced by atmospheric winds and electrical conditions. Over time, the injected material becomes dispersed, mixing with the background atmosphere through diffusion and turbulent motion. Air circulation in the mesosphere is driven by a combination of thermal gradients and wave-induced momentum transfer. Unlike the more stable stratosphere below the mesosphere, exhibits more dynamic vertical movement, although it remains less turbulent than the lower atmosphere. These circulation patterns help transport trace gases and energy across different altitudes, contributing to the overall coupling of atmospheric layers. Radiative cooling in this region is primarily driven by the emission of infrared radiation from carbon dioxide molecules. As these molecules emit energy, they lose kinetic energy, contributing to the overall temperature decrease with altitude. This process becomes more efficient in the mesosphere due to lower atmospheric density, allowing radiation to escape more readily into space without being reabsorbed by nearby molecules. The mesosphere also plays a role in filtering energy and material moving between lower and upper atmospheric regions. It absorbs and modifies upward propagating waves and partially dissipates energetic disturbances from above. This filtering effect helps regulate the transfer of energy through the atmosphere, maintaining stability across larger scales. Chemical reactions in the mesosphere are relatively slow due to low temperatures and reduced solar radiation. However, interactions involving ozone and trace oxygen species still occur, influencing local heating and cooling rates. These reactions are sensitive to small changes in temperature and composition, making the mesosphere a responsive but delicate chemical environment. The upper boundary of the mesosphere, the mesopause, represents a transition into regions where temperature begins to increase again with altitude. This reversal marks a fundamental shift in atmospheric energy balance, driven by the absorption of solar radiation in higher layers. The mesopause is not a fixed surface but a variable boundary that changes with latitude, season, and solar activity. Below the mesosphere, increasing density leads to more efficient energy transfer through collisions, gradually connecting this region to the stratosphere. This smooth transition between layers reflects the continuous nature of atmospheric structure, where no abrupt divisions exist but rather gradual changes in dominant physical processes. The mesopause forms a thin transitional boundary, where atmospheric temperature reaches its lowest global values before beginning to increase with altitude in the layers above. This reversal in temperature trend marks a fundamental shift in energy balance within the atmosphere. Below this boundary, radiative cooling dominates, while above it, absorption of solar ultraviolet energy becomes increasingly significant. The mesopause is not a fixed surface but a fluctuating zone whose altitude and temperature vary with latitude, season, and solar conditions. At this boundary, atmospheric density is low enough that collisions between molecules remain relatively infrequent compared to lower regions, yet still frequent enough to maintain partial thermodynamic equilibrium. This intermediate state allows both radiative and collisional processes to influence energy distribution. The result is a delicate balance where small changes in energy input or composition can produce measurable shifts in temperature structure. The mesopause separates the mesosphere from the lower thermosphere, and its position reflects the competing influences of cooling and heating mechanisms. In winter, polar regions' temperatures near the mesopause can become especially low due to reduced solar input and strong radiative losses. In contrast, summer conditions can produce localized warming caused by increased wave activity and energy deposition from higher atmospheric layers. Atmospheric waves play a crucial role in shaping the mesopause environment. Gravity waves generated in lower atmospheric layers by airflow over terrain or convective activity propagate upward and grow in amplitude as air density decreases. When these waves reach the mesopause, they can break, releasing energy and momentum into the surrounding gas. This process contributes to localized heating and turbulence, even in an otherwise cold region. The breaking of gravity waves also influences circulation patterns near the mesopause. Momentum transfer from these waves drives large-scale wind systems that help redistribute energy across latitudes. This dynamic interaction between wave motion and mean flow creates variability in both temperature and wind structure, making the mesopause one of the most dynamically active regions of the upper atmosphere. Chemical composition in this boundary region reflects the gradual transition from mesosphere to thermosphere. Molecular oxygen remains abundant while atomic oxygen begins to increase with altitude due to the onset of photodissociation processes driven by higher energy solar radiation. Nitrogen continues to dominate as a stable molecular component, providing structural consistency to the atmospheric mixture. Trace gases, including water vapor remnants and metallic species from meteoric ablation, also influence the mesopause environment. These trace components can participate in chemical reactions that affect local radiative properties. Even in small concentrations, they contribute to energy transfer processes that influence temperature and stability in this sensitive region. The mesopause also plays a role in the formation of noctilucent clouds, which appear at high latitudes under specific seasonal conditions. These clouds form from ice crystals that develop on microscopic particles in extremely cold temperatures. They exist in a region where sunlight can still illuminate them after sunset, creating faint visible structures that reflect the high altitude dynamics of this boundary layer. Energy transfer across the mesopause is governed by a combination of radiative emission wave dissipation and particle collisions. Infrared radiation emitted by molecules allows energy to escape upward, while incoming energy from below is modulated by wave activity and vertical mixing. This interplay determines the thermal structure of the region and maintains its status as a transition zone between cooling and heating regimes. The decrease in atmospheric density above the mesopause leads to a gradual reduction in collisional energy exchange. As a result, radiative processes become increasingly important in determining temperature structure in the lower thermosphere. This shift in dominant physical processes defines the upward transition in atmospheric behavior. Electrodynamic effects begin to re-emerge above the mesopause as ionization becomes more significant. Although still weaker than in higher regions, early stages of ion formation appear as solar radiation penetrates deeper into the atmosphere during periods of high activity. These ions interact with neutral particles, beginning the gradual re-establishment of plasma-like conditions in the layers above. The mesopause also acts as a barrier and filter for energy propagating upward from the mesosphere. Many atmospheric disturbances lose energy as they encounter this boundary, reducing their intensity before entering higher regions. This damping effect helps regulate the transmission of atmospheric waves and maintain stability in upper layers. Below the mesopause, increasing density leads to stronger collisional coupling, which smooths out temperature variations and supports more stable atmospheric layering. This contrast between the structured dynamics below and the more variable conditions above highlights the mesopause as a critical turning point in atmospheric behavior. The stratosphere begins above the mesopause and extends downward toward the tropopause, forming a region of relative stability within Earth's atmosphere. In this layer, temperature increases with altitude, a reversal of the trend observed in the mesosphere. This warming occurs because ozone molecules absorb incoming ultraviolet radiation from the sun, converting high-energy light into thermal energy that heats the surrounding air. The presence of ozone defines the chemical and radiative character of the stratosphere. Ozone forms when ultraviolet radiation splits molecular oxygen into individual oxygen atoms, which then combine with other oxygen molecules to create ozone. This cycle of formation and destruction maintains a dynamic balance that depends strongly on solar radiation intensity and atmospheric composition. Although ozone is present in small concentrations, it plays a dominant role in regulating temperature structure in this region. Air density in the stratosphere is higher than in the mesosphere, allowing more frequent molecular collisions. These collisions distribute energy efficiently, leading to a more uniform temperature distribution compared to the highly variable layers above. As a result, the stratosphere exhibits strong stratification, meaning air tends to remain in stable horizontal layers with limited vertical mixing. This stability is reinforced by the temperature gradient itself. Because warmer air lies above cooler air in this region, vertical convection is suppressed. Rising air parcels tend to cool relative to their surroundings, causing them to sink back to their original levels. This inhibits large-scale vertical motion and contributes to the layered structure that defines the stratosphere. Despite its overall stability, the stratosphere is not entirely motionless. Large-scale circulation patterns slowly transport air horizontally across latitudes. These motions are driven by temperature differences between equatorial and polar regions, which create pressure gradients that guide air movement. Over long timescales, this circulation redistributes heat and trace gases across the stratosphere. Ozone concentration is not uniform throughout this region. It tends to peak in the lower to middle stratosphere, where the balance between production and destruction is most favorable. At higher altitudes, ozone is more frequently broken down by intense ultraviolet radiation. At lower altitudes, reduced radiation limits its formation. This creates a layered distribution that influences local heating rates. The stratosphere plays a critical role in filtering harmful ultraviolet radiation. By absorbing much of the sun's ultraviolet output, it protects the lower atmosphere and Earth's surface from high-energy radiation. This absorption process not only regulates temperature but also shapes the energy balance of the entire atmospheric system. Chemical reactions in the stratosphere are relatively slow compared to lower layers due to lower temperatures and reduced moisture content. However, these reactions are highly sensitive to changes in radiation levels and trace gas concentrations. Even small shifts in composition can significantly alter ozone balance and radiative properties. Water vapor content in the stratosphere is very low compared to the troposphere. This dryness limits cloud formation and reduces the role of latent heat in energy transfer. As a result, radiative processes dominate the energy budget, with minimal interference from condensation or evaporation processes. The boundary between the stratosphere and the mesosphere above is known as the stratopause. At this boundary, temperature reaches a maximum before decreasing again with altitude. This point marks the transition between ozone-dominated heating below and radiative cooling above. The stratopause is not fixed and can shift depending on seasonal and latitudinal changes. Below the stratosphere lies the tropopause, another important boundary that separates stable upper layers from the more dynamic troposphere. The tropopause acts as a barrier that limits vertical exchange of air masses, especially water vapor and pollutants. Its height varies depending on geographic location, being higher near the equator and lower near the poles. The stratosphere also interacts indirectly with weather systems below. While it is largely decoupled from daily weather, long-term changes in its circulation can influence surface climate patterns. These interactions occur through complex coupling mechanisms involving wave propagation and energy exchange across atmospheric layers. Overall, the stratosphere represents a region of radiative balance and structural stability, shaped primarily by ozone chemistry and large-scale circulation. Its layered nature and strong temperature inversion distinguish it clearly from the more turbulent regions below. Within the stratosphere, the ozone photochemical reaction region forms a central zone where sunlight drives a continuous cycle of molecular transformation. In this region, molecular oxygen absorbs ultraviolet radiation and splits into individual oxygen atoms. These atoms then collide with other oxygen molecules to form ozone, a three-atom form of oxygen that strongly absorbs ultraviolet light. This ongoing cycle of creation and destruction maintains a dynamic equilibrium that defines both the chemical and thermal structure of the stratosphere. Ozone concentration depends on altitude, latitude, and seasonal variation. In the lower stratosphere, ozone is more stable due to reduced ultraviolet intensity, while in the upper stratosphere, stronger radiation breaks ozone apart more rapidly. The balance between these processes produces a layered distribution that shapes how solar energy is absorbed and redistributed as heat throughout the atmosphere. Temperature in this region increases with altitude because ozone absorbs ultraviolet radiation and converts it into kinetic energy. This energy is transferred through molecular collisions, gradually warming the surrounding air. As a result, the stratosphere forms a temperature inversion layer, where warmer air overlies cooler air, reinforcing atmospheric stability and suppressing vertical convection. The chemistry of ozone formation is closely tied to the presence of atomic oxygen. When ultraviolet radiation breaks molecular oxygen apart, free oxygen atoms are produced. These atoms are highly reactive and quickly combine with molecular oxygen to form ozone. However, ozone is also vulnerable to destruction through further ultraviolet exposure or reactions with other trace gases, creating a continuous cycle of formation and loss. Trace gases in this region, including nitrogen oxides and chlorine-containing compounds, can influence ozone concentration through catalytic reactions. These substances participate in chemical cycles that accelerate ozone destruction without being consumed themselves. Even in small quantities, they can significantly alter the balance of ozone production and loss, affecting the overall radiative properties of the stratosphere. The presence of ozone has a strong effect on the vertical temperature structure of the atmosphere. By absorbing ultraviolet radiation, it prevents this energy from reaching lower layers, thereby protecting biological systems at the surface. At the same time, it creates a localized heating zone that defines the thermal inversion characteristic of the stratosphere. Radiation absorption in this region is highly wavelength dependent. Shorter ultraviolet wavelengths are absorbed more efficiently, while longer wavelengths penetrate deeper into the atmosphere. This selective absorption shapes the vertical distribution of energy deposition and determines how heat is distributed across different altitudes. Molecular collisions play a key role in distributing the energy absorbed by ozone. After absorbing ultraviolet radiation, ozone molecules transfer energy to surrounding nitrogen and oxygen molecules through collisions. This process converts radiative energy into thermal motion, increasing the overall temperature of the surrounding air without producing large-scale turbulence. The stability of the stratosphere allows ozone to persist for extended periods, especially in regions where circulation is slow. However, this stability also means that changes in chemical composition can persist for long timescales. Any disruption to the balance of ozone production and destruction can therefore have long-lasting effects on atmospheric structure. Seasonal variations strongly influence ozone distribution. During periods of reduced sunlight such as polar winter, ozone production decreases while certain chemical reactions that destroy ozone can continue. This leads to seasonal thinning in specific regions, particularly near the poles. When sunlight returns, ozone production increases again, gradually restoring balance. The ozone layer is not uniform but varies in thickness and concentration across the globe. Equatorial regions tend to have higher rates of ozone production due to stronger ultraviolet radiation, while polar regions experience greater variability due to dynamic atmospheric circulation and temperature extremes. Vertical transport processes also influence ozone distribution. Air movement within the stratosphere slowly carries ozone-rich air from regions of high production to areas of lower concentration. This circulation helps maintain overall balance, but occurs on long timescales compared to faster chemical reactions. The stratopause above marks the upper limit of this ozone-dominated chemistry. Beyond this boundary, ozone becomes less stable, as ultraviolet radiation intensifies and atmospheric density decreases. Below, the influence of ozone gradually weakens as temperature and composition shift toward tropospheric conditions. The ozone photochemical region therefore represents a finely balanced system, where radiation chemistry and atmospheric motion interact continuously. Its stability depends on the persistence of this balance, which regulates both temperature structure and the protection of lower atmospheric layers from high-energy solar radiation. The stratopause forms a thin but important transition layer separating the ozone-dominated stratosphere from the more dynamic mesosphere above. At this boundary, temperature reaches its highest point in the stratosphere, before beginning to decrease again with altitude. This peak arises from the balance between ultraviolet absorption by ozone below and increasing radiative cooling and reduced ozone concentration above. Air density at the stratopause is lower than in the middle stratosphere, but still sufficient to support frequent molecular collisions. These collisions allow energy absorbed from solar radiation to be distributed efficiently across the surrounding gas. The result is a relatively stable thermal environment compared to the more variable conditions in adjacent layers. The stratopause is not a sharp physical surface, but a region where the dominant energy processes begin to shift. Below it, ozone absorption governs heating, while above it, radiative cooling and wave-driven processes begin to dominate. This gradual transition reflects the continuous nature of atmospheric structure, where changes in physical behavior occur smoothly rather than abruptly. Temperature stability near the stratopause is influenced by the vertical distribution of ozone. As ozone concentration decreases above this boundary, less ultraviolet radiation is absorbed locally, reducing heating efficiency. At the same time, the diminishing density limits the effectiveness of collisional energy transfer, allowing radiative losses to become more significant. The stratopause also plays a role in modulating atmospheric wave propagation. Gravity waves traveling upward from the stratosphere encounter changing density and temperature conditions as they approach this boundary. Some waves dissipate or break here, transferring energy and momentum into the surrounding air. This process influences local circulation patterns and contributes to variability in the lower mesosphere. The interaction between waves and mean atmospheric flow is particularly important in this region. As waves break, they deposit momentum that can accelerate or decelerate large-scale wind systems. This coupling helps regulate the overall circulation between atmospheric layers and contributes to the redistribution of energy across latitudes. Chemical composition near the stratopores reflects the transition between ozone-rich and ozone-poor environments. Ozone concentration decreases with altitude while molecular oxygen remains relatively stable. Nitrogen continues to dominate the background composition, providing a consistent medium for energy transfer and chemical interaction. Radiative processes begin to change character in this region. While ozone still absorbs ultraviolet radiation, the efficiency of this process declines with altitude due to reduced ozone density. At the same time, infrared emission from carbon dioxide and other trace gases becomes more important in cooling the surrounding air, marking a shift in the dominant energy balance mechanisms. The stratopores also influences the vertical coupling of atmospheric layers. Energy and momentum transferred across this boundary affect both the stratosphere below and the mesosphere above. This coupling is not instantaneous but occurs through a combination of wave propagation, radiative transfer, and slow advective motion of air masses. Seasonal variations affect the height and temperature of the stratopores. During different times of the year, changes in solar angle and atmospheric circulation shift the balance of heating and cooling, causing the boundary to rise or fall slightly. These variations are more pronounced in polar regions where extreme seasonal contrasts influence atmospheric dynamics. The stratopores acts as a regulatory interface in the vertical structure of the atmosphere. It limits the direct transfer of energetic disturbances between the stratosphere and mesosphere, helping to maintain distinct physical regimes in each layer. However, this separation is not absolute, as energy and matter continue to move across the boundary through gradual and continuous processes. Above the stratopores, decreasing ozone concentration leads to reduced ultraviolet absorption, allowing cooling processes to dominate once again. Below it, increasing ozone density strengthens radiative heating and stabilizes the stratified structure of the stratosphere. This dual behavior defines the stratopores as a turning point in atmospheric energy balance. The region remains sensitive to changes in solar activity and atmospheric composition. Variations in ultraviolet output or trace gas concentrations can alter the thermal structure of the stratopores, affecting its altitude and stability. Despite this variability, it consistently functions as a transition zone between two fundamentally different atmospheric regimes. The upper troposphere forms a region where atmospheric motion becomes increasingly organized into large-scale wind systems driven by strong temperature contrasts and Earth's rotation. In this layer, air is still dense enough for frequent collisions between molecules, allowing energy and momentum to be efficiently exchanged. These conditions support the development of persistent horizontal air streams that transport energy across vast distances. One of the most prominent features of this region is the jet stream, a narrow band of fast-moving air that flows near the boundary between the troposphere and stratosphere. Jet streams form where strong temperature gradients exist between warm equatorial air and cold polar air. These gradients create pressure differences that, when influenced by Earth's rotation, generate rapidly moving air currents, concentrated in relatively thin layers. The rotation of Earth introduces a deflecting influence on moving air known as the Coriolis effect. This effect causes air to curve rather than move in straight lines, shaping the structure of a large-scale atmospheric circulation. In the upper troposphere, this deflection helps organize wind into elongated bands that encircle the planet, rather than simple north-south flows. Air density in this region remains high enough to support well-defined pressure systems. These systems guide the movement of air masses and contribute to the formation of stable wind corridors. Unlike the more turbulent lower atmosphere, The upper troposphere exhibits a balance between stability and motion, allowing structured flows to persist over long distances and time periods. Temperature gradients in this region are a key driver of atmospheric motion. Warm air near the equator expands and rises, while colder air near the poles contracts and sinks. This difference creates horizontal pressure gradients that drive air movement along the boundary between warm and cold regions. The resulting flow becomes concentrated in narrow streams due to rotational constraints and conservation of angular momentum. The jet stream is not a single continuous structure, but a collection of shifting wind bands that vary in position and strength. These variations depend on seasonal changes, solar heating patterns, and interactions with lower atmospheric systems. As a result, the jet stream can meander, split, or intensify, depending on the distribution of thermal energy across the planet. Cloud formation is relatively limited in the upper troposphere compared to lower levels, but thin high-altitude clouds can still form under specific conditions. These clouds, composed primarily of ice crystals, develop when water vapor reaches saturation at low temperatures. Their presence reflects the cold and dry nature of this region, compared to the moisture-rich lower atmosphere. Energy transport in the upper troposphere occurs primarily through horizontal advection, where air masses carry heat and moisture across long distances. This process plays a crucial role in regulating global climate by redistributing thermal energy from equatorial to polar regions. Vertical motion also occurs but is more constrained than in lower layers due to increasing stability with altitude. The boundary between the upper troposphere and stratosphere, known as the tropopause, acts as a limiting layer for vertical motion. Strong temperature gradients across this boundary inhibit the upward movement of moist air, preventing most weather systems from extending into higher atmospheric regions. This restriction helps separate weather-driven dynamics below from radiatively controlled processes above. Despite this separation, wave energy generated in the troposphere can propagate upward into higher layers. These waves carry information about lower atmospheric conditions and influence circulation patterns in the stratosphere and beyond. When these waves dissipate, they transfer energy and momentum, contributing to the coupling between atmospheric layers. Moisture content in the upper troposphere is significantly lower than in lower regions due to cooling temperatures and condensation processes. As air rises and cools, water vapor condenses into clouds or precipitates out, leaving drier air at higher altitudes. This dryness influences radiative balance and limits the role of latent heat in energy transfer. The combination of temperature gradients, planetary rotation, and density structure creates a highly organized but dynamic system. The upper troposphere acts as a conduit for energy redistribution, linking surface weather systems with the broader atmospheric circulation that extends into higher layers. The transition toward the stratosphere is gradual, marked by increasing stability and decreasing vertical motion. As altitude increases, convective processes weaken, and radiative processes become more important in controlling temperature. This gradual shift defines the upper troposphere as a zone of transition between turbulent weather systems and stable atmospheric layering. The mid-troposphere represents a broad region where atmospheric energy is actively exchanged through rising and sinking air masses, forming the core of large-scale convective motion. In this layer, air density is sufficient to support frequent molecular collisions, allowing heat and moisture to be transferred efficiently between parcels of air. This creates an environment where temperature differences directly drive vertical motion, shaping the structure of weather systems across the planet. Convection in this region occurs when warmer, less dense air rises and cooler, denser air sinks. As air ascends, it expands due to decreasing pressure and cools as a result. When it descends, it compresses and warms. This continuous cycle establishes vertical circulation patterns that redistribute energy within the atmosphere and maintain thermal balance between surface and higher layers. Cloud systems often develop in this region as rising air cools to the point where water vapor condenses into liquid droplets or ice crystals. These clouds act as visible indicators of vertical motion and energy exchange. Their formation depends on temperature, humidity, and the availability of condensation nuclei, which are small particles that provide surfaces for water vapor to condense upon. The release of latent heat during condensation plays a crucial role in atmospheric dynamics. When water vapor transforms into liquid water, energy is released into the surrounding air, warming it and enhancing buoyancy. This process strengthens upward motion and contributes to the development of deeper convective systems, including large cloud formations that extend vertically through the troposphere. Mid-tropospheric circulation is influenced by both local and global factors. Local heating from the surface can trigger rising air currents, while large-scale pressure systems guide the movement of air masses across regions. These interactions create a constantly shifting pattern of airflow that connects small-scale convection with planetary-scale circulation. Moisture distribution in this region is uneven, shaped by evaporation from the surface and precipitation from higher cloud layers. As air masses move, they transport water vapor across long distances, redistributing humidity and influencing cloud formation in distant regions. This movement of moisture is a key component of the global water cycle. Temperature decreases gradually with altitude in the mid-troposphere, although the rate of cooling can vary depending on local conditions. Areas with strong convection may experience slower cooling due to the release of latent heat, while more stable regions exhibit more uniform temperature gradients. This variability contributes to the complexity of atmospheric structure in this layer. Air pressure continues to decrease with height, reducing the density of the atmosphere and influencing the behavior of rising air parcels. As pressure drops, air expands, leading to cooling that can either enhance or suppress convection, depending on moisture content and environmental conditions. This interplay determines whether clouds will continue to grow or dissipate. The mid-troposphere also serves as a region of energy redistribution between surface-driven processes and upper atmospheric circulation. Heat absorbed at the surface is transported upward through convection, while energy from higher layers can influence stability and vertical motion. This bidirectional exchange helps maintain the overall balance of atmospheric energy. Wind patterns in this region are less organized than in the upper troposphere, but still influenced by larger circulation systems. Air masses move in response to pressure gradients, often interacting with developing storm systems and frontal boundaries. These interactions contribute to the formation and evolution of weather systems. Turbulence is common in the mid-troposphere due to the interaction of rising and sinking air masses. This turbulence enhances mixing, allowing heat, moisture, and momentum to be redistributed more efficiently. It also contributes to the variability of cloud formation and atmospheric stability. The mid-troposphere plays a central role in connecting surface conditions with higher atmospheric layers. Energy and moisture originating at the surface are transported upward, while influences from above, such as jet stream dynamics, can affect stability and circulation patterns below. This makes the region a critical interface in the vertical structure of the atmosphere. As altitude increases within the mid-troposphere, convective activity gradually weakens due to decreasing moisture content and temperature. Air becomes less capable of sustaining strong vertical motion, leading to a transition toward more stable atmospheric conditions in the upper troposphere. This gradual shift reflects the continuous nature of atmospheric layering rather than abrupt separation. The lower troposphere forms the atmospheric layer closest to Earth's surface, where direct exchanges of heat, moisture, and momentum between land, ocean, and air shape the fundamental structure of weather. In this region, Air density is at its highest within the free atmosphere, allowing frequent molecular collisions that efficiently distribute energy and establish strong thermodynamic coupling with the surface below. This close coupling makes the lower troposphere the primary driver of daily weather variability. Energy in this layer originates largely from solar radiation absorbed by Earth's surface. The surface then transfers this energy into the atmosphere through conduction, convection, and radiation. Warm air rises as it becomes less dense, while cooler air descends to replace it, establishing continuous vertical circulation. This process is strongly influenced by surface conditions such as land cover, ocean temperature, and terrain structure. Moisture plays a central role in the behavior of the lower troposphere. Water evaporates from oceans, rivers, lakes, and soil, entering the air as invisible vapor. This vapor is transported by wind and vertical motion, redistributing latent energy across regions. When conditions change, the vapor condenses into clouds or precipitation, releasing stored energy back into the atmosphere and influencing local temperature and stability. Cloud formation in this region is frequent and varied. Depending on temperature and humidity, clouds can form as low-level sheets, towering vertical structures, or scattered patches. These clouds regulate the amount of solar radiation reaching the surface by reflecting incoming light and trapping outgoing infrared radiation, thereby influencing the energy balance of both atmosphere and ground. Temperature in the lower troposphere generally decreases with altitude, a result of decreasing pressure and expansion of rising air. However, this gradient is constantly modified by surface heating, moisture content, and atmospheric mixing. Local variations can produce inversions, where warmer air overlays cooler air, temporarily altering normal vertical structure and affecting pollution dispersion and cloud development. Wind in this region is strongly influenced by surface friction. As air moves across land and water, it slows and changes direction due to interactions with terrain and surface roughness. This frictional effect creates turbulence, which enhances mixing and helps distribute heat and moisture more evenly across the lower atmosphere. The boundary between land and air is a zone of intense energy exchange. Solar radiation heats the surface, which in turn warms the air directly above it. At night, the surface loses heat through infrared radiation, cooling the adjacent air and sometimes producing stable layers near the ground. These daily cycles drive rhythmic changes in atmospheric structure. The lower troposphere also contains most of Earth's atmospheric water vapor. This concentration of moisture makes it the primary region for cloud formation and precipitation processes. The availability of water vapor varies with temperature, surface conditions, and air mass movement, leading to spatial and temporal variability in humidity. Pressure decreases rapidly with altitude in this layer, causing strong gradients that drive vertical motion. Rising air expands and cools while sinking air compresses and warms. These processes form the basis of convection, which powers many weather systems, including storms and precipitation events. Air masses in the lower troposphere often carry distinct temperature and moisture characteristics depending on their origin. When these air masses meet, they form boundaries known as fronts, where sharp changes in weather conditions can occur. These interactions are key drivers of dynamic weather patterns across regions. Turbulence is especially strong near the surface due to friction and uneven heating. This turbulence enhances mixing between air layers, smoothing temperature differences and distributing moisture. It also influences the dispersion of particles and gases released from natural and human sources. The lower troposphere acts as the most active interface between Earth's surface and the rest of the atmosphere. It responds rapidly to changes in surface conditions and drives much of the short-term variability in climate and weather. Despite this variability, it remains tightly linked to the layers above through continuous exchange of energy and mass. As altitude increases, the influence of surface heating gradually weakens, and atmospheric conditions become more stable. This transition marks the movement toward the mid-troposphere, where large-scale circulation begins to dominate over direct surface-driven processes. The planetary boundary layer forms the lowest portion of the atmosphere directly influenced by the surface through continuous exchange of heat, moisture, and momentum. This layer responds rapidly to changes in surface conditions, including variations in solar heating, terrain structure, and surface roughness. Because of its proximity to Earth's surface, it experiences the strongest turbulence within the atmosphere, driven by frictional forces and uneven heating. Air in this region is in constant motion, shaped by mechanical turbulence, generated as wind flows over landforms, vegetation, buildings, and bodies of water. This friction slows the wind and creates chaotic eddies of varying size which mix air vertically and horizontally. At the same time, thermal turbulence arises when sunlight heats the ground unevenly, causing warmer air to rise and cooler air to sink in localized circulation patterns. Energy exchange in the boundary layer occurs through multiple pathways. Solar radiation warms the surface during the day, and this heat is transferred into the air above through conduction and convection. At night, the surface cools by emitting infrared radiation, which cools the air in contact with it and can lead to the formation of stable layers near the ground. Moisture dynamics are especially active in this layer. Evaporation from soil, vegetation, and water bodies continuously adds water vapor to the air. This vapor mixes through turbulent motion and can condense into fog or clouds when temperatures drop or humidity increases. These processes contribute to rapid changes in local weather conditions. Temperature structure in the boundary layer is highly variable. During daytime, heating temperature often decreases with height, promoting convection and vertical mixing. At night, radiative cooling of the surface can reverse this gradient, creating temperature inversions where cooler air is trapped near the ground beneath warmer air aloft. These inversions can significantly reduce vertical mixing and trap pollutants near the surface. Wind speed and direction in this layer are strongly affected by surface friction. As air moves across different types of terrain, it experiences resistance that slows its motion and alters its path. This interaction produces complex flow patterns that vary depending on surface characteristics such as vegetation density, urban structures, and topography. Turbulence within the boundary layer plays a key role in redistributing energy and material. It breaks down large-scale gradients in temperature and humidity, mixing air masses and smoothing spatial differences over time. This mixing helps regulate surface climate conditions and influences the development of clouds and precipitation. The height of the boundary layer is not constant and varies depending on time of day, season, and surface conditions. During the day, strong surface heating can cause the layer to expand as warm air rises and mixing intensifies. At night, cooling leads to a reduction in turbulence and a shallower layer with more stable conditions. This layer also acts as the primary interface for exchanges of gases and particles between Earth's surface and the atmosphere. Natural emissions from vegetation, soil, and oceans, as well as human-generated emissions, enter the atmosphere here and are rapidly dispersed through turbulent motion. This process determines the initial distribution of atmospheric constituents before they are transported to higher layers. Radiative processes interact with turbulent mixing in complex ways. While turbulence redistributes heat mechanically, radiation governs the gain and loss of energy at the surface and in the air. The balance between these processes determines the stability of the boundary layer and influences whether convection will develop or be suppressed. The planetary boundary layer is also the region where most weather begins. Small-scale variations in heating and moisture can grow into larger systems when conditions support sustained convection. These processes link surface conditions directly to atmospheric dynamics in higher layers, forming the foundation of weather system development. As altitude increases, the influence of direct surface forcing diminishes. Turbulence weakens, mixing slows, and the atmosphere transitions toward the more organized flow patterns of the mid-troposphere. This gradual change reflects the continuous nature of atmospheric structure, where no sharp boundary separates surface-driven dynamics from broader atmospheric circulation. The surface-atmosphere exchange interface represents the direct boundary, where Earth's solid and liquid surfaces interact continuously with the overlying air. This region is defined by immediate transfer of energy and matter through conduction, evaporation, condensation, and radiation. Unlike higher atmospheric layers where processes are shaped primarily by radiation and large-scale motion, this interface is governed by intimate contact between air molecules and surface materials. At the ground level, solar radiation is absorbed differently depending on surface type. Dark soils, vegetation, water ice, and urban materials each respond uniquely to incoming energy. These differences create spatial variations in heating that directly influence the air above. As surfaces warm, they transfer energy to adjacent air molecules through collisions, increasing air temperature and initiating vertical motion. Evaporation is a dominant process in this interface, especially over water and moist soil. When liquid water gains sufficient energy, individual molecules escape into the air as vapor. This phase change removes heat from the surface, producing a cooling effect while increasing atmospheric moisture. The vapor then mixes into the boundary layer, becoming available for cloud formation and precipitation processes higher up. Condensation occurs when moist air near the surface cools, often during nighttime or in shaded regions. As water vapor transitions back into liquid form, energy is released into the surrounding air, slightly warming it. This exchange of latent heat plays a crucial role in regulating local temperature and humidity conditions. Radiative exchange is constant at the surface interface. Incoming solar radiation warms the ground during the day, while outgoing infrared radiation allows the surface to lose heat, especially at night. The balance between these two forms of radiation determines the diurnal temperature cycle, which strongly influences atmospheric stability in the lowest layers. The interaction between surface roughness and airflow shapes how momentum is transferred into the atmosphere. Smooth surfaces like water allow air to flow more freely, while rough surfaces such as forests or urban environments create greater resistance. This resistance generates turbulence, which enhances mixing and redistributes energy and moisture. Heat stored in the ground also plays a role in this interface. Soil and rock can absorb energy during the day and release it slowly over time. This delayed release moderates temperature changes in the air above, reducing extremes and contributing to the persistence of local atmospheric conditions after sunset. The exchange of gases is another important feature of this boundary. Carbon dioxide, oxygen, water vapor, and trace gases move between the surface and atmosphere depending on biological activity, temperature, and physical conditions. Vegetation plays a key role in regulating this exchange through processes such as photosynthesis and respiration, which continuously alter atmospheric composition at local scales. Near the surface, atmospheric stability is highly sensitive to small changes in energy balance. Slight increases in surface heating can trigger rising air currents, while small decreases can stabilize the air and suppress vertical motion. This sensitivity makes the interface a critical control point for the development of weather patterns. The interaction between liquid water and air is particularly dynamic over oceans and large water bodies. Waves and currents constantly expose new surface areas to the atmosphere, enhancing evaporation and gas exchange. This continuous renewal of the surface makes oceans a major source of atmospheric moisture and thermal regulation. In colder regions, the surface interface can include ice and snow, which reflect much of the incoming solar radiation. This high reflectivity reduces surface heating and limits energy transfer to the atmosphere above. As a result, air near icy surfaces tends to remain colder and more stable, influencing regional atmospheric circulation. Dust aerosols and microscopic particles are also exchanged at this boundary. These particles can be lifted into the atmosphere by wind or settling from above, and they influence cloud formation by acting as nuclei for condensation. Their presence affects both radiative properties and chemical reactions in the lower atmosphere. The surface-atmosphere exchange interface is not static but changes continuously with time. Daily cycles of heating and cooling, seasonal variations in solar angle, and long-term climate shifts all modify how energy and matter move across this boundary. Despite this variability, it remains the primary gateway through which Earth's surface communicates with the atmosphere. As altitude increases away from the surface, the direct influence of ground-based processes weakens. Turbulence decreases, radiative balance becomes more dominant, and the atmosphere transitions into the more structured dynamics of the planetary boundary layer above. The near-surface radiative balance zone represents the final layer of atmospheric interaction, closest to Earth's energy source and energy sink system. In this region, incoming solar radiation and outgoing terrestrial radiation are continuously exchanged between the surface and the lower atmosphere, establishing the fundamental energy equilibrium that governs temperature and climate conditions. This balance is not static, but constantly adjusted through changes in surface properties, atmospheric composition and cloud coverage. Solar radiation reaching the surface is partially absorbed and partially reflected depending on the characteristics of the ground and lower atmosphere. Surfaces such as water and vegetation absorb a significant portion of this energy, while lighter surfaces like ice and sand reflect more of it back into the atmosphere. The absorbed energy is then redistributed through heating of the ground and air driving convection and influencing local atmospheric motion. The surface emits infrared radiation as it cools, releasing energy back into the atmosphere and eventually into space. Greenhouse gases in the lower atmosphere, including water vapor, carbon dioxide, and methane, absorb a portion of this outgoing radiation and re-emit it in all directions. This process slows the direct loss of heat to space and helps maintain a stable range of surface temperatures. Energy exchange in this zone is highly sensitive to atmospheric composition. Small changes in greenhouse gas concentrations can alter the efficiency of infrared absorption and emission, shifting the overall energy balance. This sensitivity makes the near-surface region a critical regulator of planetary temperature stability. Clouds play a significant role in radiative balance. They reflect incoming solar radiation, reducing surface heating during the day while also trapping outgoing infrared radiation, reducing cooling at night. The net effect of clouds depends on their type, altitude, and thickness, leading to complex influences on local and global energy budgets. The lower atmosphere above this zone acts as both a reservoir and mediator of energy. Heat absorbed at the surface is stored temporarily in the air and redistributed through turbulence and convection. This redistribution smooths temperature differences across regions and timescales, contributing to the moderation of extreme temperature variations. Humidity strongly influences radiative balance. Water vapor is a powerful absorber of infrared radiation, enhancing the greenhouse effect in the near-surface atmosphere. As moisture levels increase, more heat is retained within the lower atmosphere, altering the rate at which the surface cools during nighttime periods. The interaction between radiation and convection defines the stability of this zone. When surface heating is strong, rising air enhances convective mixing, distributing heat upward. When radiative cooling dominates, air near the surface becomes denser and more stable, reducing vertical motion and allowing temperature inversions to form. Daily cycles create a rhythmic pattern of energy exchange. During daylight hours, solar heating drives upward motion and atmospheric mixing. At night, radiative cooling stabilizes the lower atmosphere, often leading to calm conditions and the formation of dew or fog as moisture condenses near the ground. The near-surface radiative balance zone also influences broader atmospheric circulation. Differences in heating between regions create pressure gradients that drive wind systems, which in turn redistribute energy and moisture globally. This connects local radiative processes directly to planetary-scale atmospheric dynamics. Aerosols and fine particles in this region affect radiative transfer by scattering and absorbing both incoming and outgoing radiation. These particles can originate from natural sources such as dust and sea spray, or from biological and geological processes. Their presence modifies visibility, temperature distribution, and cloud formation processes. Surface heterogeneity introduces additional complexity. Variations in terrain vegetation and water coverage create uneven heating patterns that influence local airflow and cloud development. These variations contribute to the diversity of microclimates observed across different regions of the planet.